So up to now, there's been a lot of discussion about these four kinematics equations and where they come from. So I'd like to get to a point where we put these kinematics equations into practice and show how they can be useful in solving problems related to motion. So when it comes to problem solving in physics, the biggest piece of advice I have for you is to spend more time setting up the problem than solving the problem. And I'm going to choose two example problems where I'll try to illustrate that approach. So a little story behind the first problem. So the person you see here, this is my former physics professor. It turns out I was a physics student at Saddleback College as well. And so this is my professor, Bob Parsons. He often talked about his son, Mike Parsons, and he's a little bit famous. He was a pioneer in big wave surfing. So this is a picture of Mike Parsons surfing a 60-foot wave at a place called Jaws in Hawaii. And I remember my professor telling me a story at one point that his son Mike had earned his pilot's license so that he could fly to remote parts of the globe to track down some of these big waves. And I don't know, it just conjured up an image to me of him trying to land on some sketchy dirt runways somewhere in some remote part of the world. And that begs the question of how safe would you feel landing on a dirt runway in a foreign land? A Cessna aircraft can only continue flying safely as long as it's above its stall speed. And I've looked it up. I think it's reasonable to guess that the stall speed of a Cessna might be about 80 miles per hour. So probably the speed with which the wheels on the plane touch down we'll assume is just a little bit higher than that, but maybe not too much more. You don't want to land too fast because the runway has a finite length to it, and it's also harder to control the plane when the wheels touch down, but you can't touch down any slower than this or else you'll actually plummet out of the sky. So we'll take this to be the initial speed with which an aircraft lands on a runway. And so the question becomes, what's the minimum safe length of a runway? Because after all, it takes a lot of work to clear away all the brush and debris and rocks and make it level and create a runway for an airplane. So the shorter it is, the more time and money you save in making that runway. So what's the shortest you can get away with? One more piece of information I can give you is that at best, it's safe to assume this aircraft's maximum deceleration in magnitude is about 1.5 Gs. So what's that mean? To measure acceleration in units of Gs. Well, from the ruler drop experiment, you know that gravity causes an object to accelerate at 9.8 meters per second. So when we measure acceleration in Gs instead of meters per second, we're just expressing it as multiples of this numerical value. So 1.5 Gs would be the same thing as 14.7, I believe. What's 1.5 times 9.8? Yeah, 14.7 meters per second. Okay, so that's it. The question at hand is, what's the minimum safe length of a runway for an aircraft is if its touchdown speed is 80 miles per hour and its maximum deceleration is 14.7 meters per second. So how do I spend more time setting up the problem than solving the problem? Well, the first step in all this is to turn it into a picture. And I know there's a photograph of this, but what I really mean is a motion diagram. So let's assume that the airplane is moving in the positive direction. So identify an x-axis. You don't have to be a great artist here, just anything that somewhat represents an airplane. So there it is, touching down with some initial velocity at the origin and then traveling forward, and we're being asked for the minimum value of delta x. So you notice that this picture tells us pretty much all the information that this word problem that I expressed to you says, right? We know the initial speed. If I label some other values here, if I say the acceleration is 14.7, now I might have stated in an earlier video that acceleration and velocity are vector quantities. And vectors not only have magnitudes, but they have a direction. And when it comes to motion along a straight line, we can express direction instead of using words like to the right or to the left or saying to the east or to the west. We can express direction just with a positive or a negative sign. So although the plane is moving toward the positive direction on the x-axis, the acceleration is an attempt to slow the plane down and force it to reduce its speed, so the acceleration actually points toward the negative x-axis. So I'm going to say the initial velocity is positive 80, oh, I said miles per second, not a chance. Sorry about that. 80 miles per hour, and the acceleration is negative 14.7 meters per second. So I think this picture says everything that the initial word problem said, right? Make it a graphical representation of the problem at hand. Spend more time setting up the problem than solving the problem. Here's another thing I can do. Knowing that this is a problem in kinematics, and kinematics always relates the same set of 5 variables: distance, time, initial velocity, final velocity, and acceleration, I might as well go ahead and make a list of all those variables and see if I can identify the correct numerical values and units that go along with them. So number one, I can identify what's the quantity I'm trying to solve for. So we're trying to find the length of the runway. There's no mention of time in this problem, but we are told that the initial velocity is positive 80 miles per hour when it first touches down. And then we always have to make notes, okay? So that's another part of setting the problem up. You're welcome to add what you're inferring to the problem. So we can state what's implied. It's implied that the final velocity equals 0 in the limiting case, right? The airplane's going to make it to the end of the runway, and just before it starts to go off into the bushes at the end of the runway, it reaches a state of rest at the very end. So that wasn't initially explained in the problem, but that's something that has to be inferred or assumed. So final velocity is 0, and the acceleration is negative 1.5 g, which in turn is equal to negative 14.7 meters per second. Oh, and at this point, I think I need to give you a little trick method to keep in the back of your head. We always want to convert units into meters and seconds and meters per second and so on. We want things to be metric. So we have to convert this to meters per second. And I'm sure you can do some dimensional analysis and figure this out, knowing that there are 60 minutes in an hour and 60 seconds in a minute. And you probably know there's 5,280 feet in a mile, and there's 3.28 feet in a meter. You can go through and figure out how to calculate it, but I'll give you a shortcut. 80 miles per hour is the same thing as 36 meters per second. And I did that by, in my head, really quickly, taking the value in miles per hour and just dividing it by 2. That gave me 40. And then I knocked off 10% of that, so 40 minus 4, and that's where I got the 36. So in the same way, if there was a problem that said an object was going 60 miles per hour, you can very quickly realize that's the same thing as 27 meters per second, right? Cut it in half, and that gives you 30, and then take off 10% of that result, and that gives you 27. So real quick, off the top of your head, see if you can convert 100 miles per hour into some number of meters per second. I'll give you a moment. Hit pause if you need to. Right, okay, so 100 miles per hour is 45 meters per second, right? Cut it in half to get 50, then take off 10%, and there you go. So just a side note, maybe you can keep that in mind. You're going to have to do a lot of unit conversion throughout this semester, and often you'll have to change miles per hour to meters per second, so there's the shortcut I offer for you. Anyway, back to the problem at hand. We're spending more time setting the problem up than solving it. We've made a diagram that represents the word problem. We've made a list of quantities that are asked for and given or implied. And the next step would be figure out what a useful equation would be. And one way to do that is just to brainstorm all the equations you know, right? You don't have to pick the exact correct equation, just lay out in front of you all the possible equations. So let's list all the kinematics equations. Delta x equals 1/2 v naught plus v multiplied by t. Final velocity is initial velocity plus acceleration times time. Distance is equal to initial velocity times time plus 1/2 acceleration multiplied by time squared. Final velocity squared is initial velocity squared plus 2 times acceleration times displacement. Okay, so now that I have all the possible equations laid out in front of me, I can compare them with the list that I've built. And because time wasn't given or asked for in this problem, then I want to try to find the one kinematics equation that doesn't have time in it. Well, this one has time, this one has time, this one has time, but our fourth kinematics equation does not have time anywhere in it. So this one would be very useful for a problem like this. Now, we have to solve for the length of the runway, which is the delta x. So now we're kind of at the point of solving the problem and past setting it up, right? Setting it up involves drawing diagrams, making lists, converting units, stating implied values, brainstorming on possible equations, and at that point we need to start to solve. But even when we solve the work, we want to do it well, very clearly and take a step-by-step approach. So if you're impulsive, you start to plug in the numbers. Let me show you the wrong way to solve this problem from here. The wrong way would be to start plugging in numbers. 0 equals 36 squared plus 2 times negative 14.7 times delta x. And then solve. Take my advice. Don't plug the numbers in. Save that for the very last step of your work. Do the algebra to isolate for the variable, and then, and only then, as a final step, plug the numbers in. So let's take that approach. I guess what I need to do is subtract initial velocity squared from both sides of the equation. So if our initial statement of the equation is step 1, then in step 2, we can say 2a delta x is equal to v squared minus v initial squared. In the next step, I'll divide both sides of the equation by 2a. So now we have delta x is v squared minus v initial squared divided by 2a. Okay, so now I get to plug the numbers in. All right, so the length of the runway is equal to 0 meters per second, quantity squared, minus 36 meters per second, quantity squared, divided by negative 14.7 meters per second. I guess at this point I can call this meters per second squared. Notice I'm not just plugging in numbers, I'm also plugging in the units. Now this is useful in problem solving and is another hint I have. Beyond spend more time setting it up than solving, I should also add include units as another problem-solving strategy. By including the units along with the numbers, you can see if your work is at least dimensionally correct. In the end, if we don't get meters as a final result, then we're using the wrong equation. And so if the units don't combine correctly, then we know our numerical answer is incorrect. So it's sort of a safety net to include the units along with your work. And in fact, before you even reach for a calculator, check and see that the units work out. Of course, 0 anything squared is going to give you 0. So we have delta x is equal to, now, regardless of the number in the numerator, because we're squaring, we're going to end up with meters squared divided by seconds squared. And I think at this point, we can get away with noticing that this minus sign and this negative are going to cancel out. Anyway, in the denominator, we have meters per second squared. So you see that the square seconds and square seconds cancel out, and now we have a square meter divided by a meter, which indeed gives us meters. So now that we know dimensionally the equation is correct, now you can reach for a calculator and do the numerical part. we just need to do 36 squared divided by 14.7. So if you're calculating along with me, I think you'll agree that our delta x comes out to 88.163266, so on and so on. And as we said, the answer is meters. Now this brings up the question of sig figs. I don't care. Sig figs don't matter, all right? You can take a deep breath and a sigh of relief and realize you don't have to worry about sig figs for the most part in this class, unless we're doing labs. Now, in labs, we're making measurements. And whenever you make a measurement, you have to use some sort of tool to make that measurement. Tool. And there's no perfect measurement tool. And so the precision that's built into that tool is going to be the guiding factor behind the number of sig figs you should report in your measurement. So bottom line is, unless the numerical value you're writing on the paper expresses a measurement that you made in a lab, then you're not responsible for keeping track of sig figs. So in all of your homework and example problems and hypotheticals, you can round off wherever you want. Now, it might be nice to keep all the information from the exact number in case you have to carry on with the computation and substitute this answer into the next step of the problem. But once you get to your final answer, you can just round this off, and if it feels good to you to call this 88.2 meters, then call it 88.2. If you want to round off and just call it 88 meters, that's good enough as well. So no problem. Either way, it's not going to change all of this work that you presented. It's not going to change the diagram that you drew or the list that you made or the unit conversion that you completed. It's not going to change your brainstorming process or all the algebraic work you got to the answer. Whether or not your final answer goes to the 10th place or the single digits place doesn't really make any difference as far as I'm concerned. So the last step would just be to think about whether or not your answer is reasonable before you accept it. 88 meters. A meter and a yard are roughly the same thing, so this would be a little bit shorter than a football field, and I suppose that's a reasonable enough answer. I feel good about it. We'll put a box around it. Now, I would hope that my runway is longer than that, because I don't, as a pilot, I wouldn't want to have to aim and make sure I'm touching down at the very beginning of the runway, and then I put on the brakes and get the best deceleration I could possibly get so that I just barely escape death by reaching zero only at the very end. I would hope that the runway is a little bit longer at the front end and at the back end to give me some room for error. And I'm also not going to rely on the fact that I can always achieve my very best deceleration. So in the very limiting case, 88 meters would be the best, but I would feel a lot better if I bumped that up by a factor of 2 or maybe even a factor of 3 for the safety measure. But then you get back into the practical situation of it's going to cost more and take more man hours to make that happen. But that's besides the point of this example problem. So let's do one more example problem, and then we'll move on to the next lesson. So see if you can turn this word problem that I'm reading to you into a diagram. I'll read it a couple times over. So the problem goes something like this. A car is initially driving down the freeway with a speed of 60 miles per hour. And then the car in front of it's going a little too slow. So the car going 60 miles per hour moves over one lane and then uniformly accelerates up to 80 miles per hour, and in doing so passes the slower vehicle. And as it goes from 60 miles per hour to 80 miles per hour uniformly, it covers a distance of 126 miles down the freeway. How much time did the car spend during this moment of acceleration? Now, if you're able to answer that off the top of your head without going through this problem-solving approach, then you're probably ready to move on to a higher level physics course than this. In fact, most of you would probably like to hear that problem read again so you can decipher all the key information. So the same way, if you were reading this out of a textbook, you would want to reread the problem until you're certain all the values that are being given here. So I'll read it one more time. A car is initially driving 60 miles per hour down the freeway, and in order to pass another vehicle, it uniformly accelerates up to 80 miles per hour. The car travels 126 meters down the freeway during this maneuver. How much time did the car spend accelerating? So, at the very least, we know this is about a car moving in one dimension. So, spend more time setting up the problem than solving the problem. The first step of that is always to draw a motion diagram. So we'll picture a car traveling down the x-axis in the positive direction. Initially, that car is going 60 miles per hour. It's going to travel straight ahead down that segment of highway. You don't have to be a good artist, you just have to turn it into some sort of picture. And in the end, its final velocity is up to 80 miles per hour. It traveled a distance of 126 meters, and we're asked for the amount of time. So you can see this picture says everything that I read out loud, and you can take it in all in one view. It's even though there are all these symbols here, it's kind of nice to rewrite all of this in one list going down the page. Delta x, t, v initial, v final, and acceleration. 126 meters. We're asked for the amount of time. The initial velocity is given as positive 60. That positive is just a reminder that it's moving to the right. The final velocity is also positive. It's 80 miles per hour. And the acceleration wasn't given or asked for, so I can cross it out. Okay, and then you can use my trick. 60 miles per hour is the same as 27 meters per second, and 80 miles per hour is the same as 36 meters per second. So now all of our units agree. So the next thing is to brainstorm on possible equations. Delta x equals 1/2 v naught plus v multiplied by t. V equals v naught plus at. Delta x equals v squared equals, I'll leave it up to you to see if you remember these equations, but you probably already noticed now that I think these equations both have acceleration in them. You be the judge. I know this one does. The very first one I wrote does not have acceleration, and I know I want the equation that doesn't have acceleration in it, so I think we found the equation we want to use. So all of the setting up the problem here is done now. We've drawn the diagram, we've made a list, we've converted units, we brainstorm on our equations, and now we need to do the solution. But again, don't jump into number crunching. Don't write out 126 equals 1/2 of 27 plus 36 times t. There's two problems with that. One, we always want to do the algebra with the variables in place, not the numbers. And two, this is discounting the units. This is only the numbers without their units. So don't be impulsive and jump ahead. Take your equation as step one and show each step of your algebra along the way. So we're going to multiply both sides of the equation by 2. 2 delta x is equal to v naught plus v multiplied by t. We're going to divide both sides of the equation by v naught plus v. And so in our third step, we get t equals 2 delta x over v naught plus v. So finally, we can plug in the numbers along with their units. And the time it takes for the car to make this passing maneuver on the freeway is going to be 2 multiplied by 126 meters divided by 27 meters per second plus 36 meters per second. 2 times 126 is 252, I believe. And 27 plus 36 gives us 63 meters per second. Let's check out the units before we worry about the numbers. Meters cancel with meters, and so what we really have is 1 over seconds, which in the end is just seconds. Thank goodness, because we are trying to solve for time. So reach for a calculator and divide 252 by 63, and you get 4 seconds. Oh, that's nice. Now we don't even have to worry about rounding off. It came out to be a perfect round number. So there you have it. This is what I mean when I say spend more time setting up the problem than solving the problem, and don't forget to include the units with your work.